All right, let's talk about factoring. But I want you to forget everything you might remember from algebra class. We're going to throw out the calculator for this one. Instead, we're going on a geometric journey to see numbers not as symbols, but as actual shapes you can build and move around. It's a whole new way to see what's really inside a number.
So here's the big question that kicks this all off. What if you could actually see the factors of a number? I mean, not just calculate them, but discover them by rearranging shapes. It might sound a little strange to us today, but this visual way of doing math, well, it goes all the way back to the ancient Greeks.
So let's dive in. We're going to start by connecting a really simple algebraic identity to this powerful geometric idea, one that was fundamental to how Greek mathematicians actually visualized multiplication, and its opposite, factoring. Okay, everything hinges on this one beautiful formula, the difference of squares. It basically says that any odd number, we'll call it n, can be written as x squared minus y squared. And if you remember your algebra, you know that that expression always factors out to x minus y times x plus y. So all of a sudden, the problem of factoring n isn't about division anymore. It's a hunt for two perfect squares.
So that's the algebra, but how do we turn that into something you can actually build? How do we see it? Well, we're going to build the shape of our number using a method straight out of Euclid's playbook, and it involves a shape with a really cool name, a gnomon. The whole process starts with a big square. Let's say its side length is x. Now, there's a trick to picking the right size for x. It has to be the very first whole number that's just a little bit larger than the square root of n, the number we're trying to factor. This just guarantees that our starting area, x squared, is bigger than n, which gives us something to subtract from. Okay, next up, in a purely geometric move, we're going to slice a smaller square, this one with a side length of y, right out of the corner of the big one. This little cutout is what's going to let us shrink the total area down to our target number. And this is where it all clicks. The leftover area, this cool L shape, is called a gnomon, and its area is precisely the area of the big square minus the area of the small one we just removed. In other words, its area is x squared minus y squared. So here's the crucial part, the real aha moment. If we can adjust the size of that cutout square just right so that the gnomon's area becomes exactly equal to our number n, then we've done it. We've solved the puzzle. The lengths that make up that L shape, which are x minus y and x plus y, are literally the factors of n. Okay, so this isn't just some abstract theory. Let's see how this builds into an actual, practical, step-by-step recipe. This is a real process you could actually do with a ruler and a compass. Totally old school. All right, here's the game plan. First, you pick your starting square, x. Then, you start a search. You try one size for the cutout square, y. And you calculate the gnomon's area. Is it a match? Nope. Okay, you shrink y by 1, and you try again. And you just keep doing this step by step until that L-shaped area is exactly n. The moment it is, you stop. The side lengths that form that shape, those are your factors. And the real elegance of this method is how self-contained it is. As the source material puts it so nicely, no sieves, no extra primes, just squares and gnomons. You're only manipulating areas until they match. It's just a beautifully pure, geometric approach. Now, that search method is incredibly elegant, but let's be honest, it could be kind of slow. You might have to try a lot of different squares before you find the right one. So what if you could skip that whole search? What if a single, perfectly chosen angle could solve the puzzle instantly? So let's compare these two geometric ideas. On one hand, you've got the gnomon method. That's a patient search, an iterative process of adjusting areas. But the angle method, that promises a direct placement, a single geometric construction that could reveal the answer without any trial and error at all. So how would this even work? The idea is you build a very special triangle. Using a rule called the law of cosines, you construct it so one of its sides is related to your number n. The magic is supposed to be in one of the angles. If you could just construct the right angle, the geometry of the triangle would literally force the other two side lengths to snap into place as the factors of n. But how on earth do you find that magic angle? This sounds incredible, right? Almost like magic. A single angle that solves factoring? But there's a catch. There's a hidden secret inside this supposed geometric shortcut that we really need to unpack. So is it really a true shortcut? Can we just pick any angle and find the factors of any number from scratch? Or
is there something else going on here?
And here's the secret. The angle doesn't find the factors for you, it's built using one of them. To construct that perfect angle, the formula actually requires you to already know a factor, d. You're essentially telling the triangle the answer from the very beginning, so this method doesn't discover the solution, it just beautifully represents a solution you already have.
So, while the angle method isn't some magical shortcut for finding unknown factors, it does give us a profoundly different lens for understanding them. It shows that factors aren't just an algebraic property, they are deeply woven into the geometric fabric of a number. It's all about perspective.
And that leaves us with a final thought. This whole journey, from gnomons to angles, is such a powerful reminder that a shift in perspective can completely transform how we look at a problem. It really makes you wonder, what other truths in math or anywhere else are out there just waiting not to be calculated, but to be truly seen?